More and more enterprises and service providers are moving to IP-based storage architectures, like those deployed in the cloud. The proliferation of Ethernet interfaces at 10 gig and faster provide a viable alternative to expensive and complex fiber channel networks, which have diminished in popularity due to the increased capital and operational expenses required to run these dedicated networks over completely separate infrastructure. As the performance of Ethernet has caught up to and now surpassed fiber channel, the traditional argument that storage requires the speed and lossless conditions of fiber channel are no longer compelling. IP over Ethernet is now the interconnect of choice for the most demanding storage environments. Coupled with the increased availability of high-speed and low-cost Ethernet in the data center, there has been an explosion of new technologies which leverage Ethernet as a transport to deliver storage architectures at unparalleled speeds and capacity, all while providing significant price advantages over legacy architectures. The most obvious example is the availability of cloud-based storage offerings. With pricing as low as 1 cent per gigabyte, cloud storage offers large volume and storage at incredibly attractive pricing. To maintain this structure, cloud providers have turned to scale-out storage architectures, which leverage their high-capacity IP Ethernet infrastructure to store and deliver data at previously unimaginable scales. While advantageous from the perspective of volume, cloud-based architectures remain unsuitable for high-performance storage, such as block access as delivered by a legacy fiber channel SAN. Where high-performance block storage is required for enterprise data, next-generation flash arrays are delivering incredibly high-performance access to data over 10 gigabit Ethernet networks, accessed typically via iSCSI. Some examples of high-performance flash systems include Pure Storage, EMC, and NetApp with their SolidFire solution. Leveraging the storage principles of the cloud, other vendors, such as EMC with their Scale.io solution, have used software which runs on server infrastructure to create large virtual SANs by reclaiming direct attached storage on servers. A third approach to high-performance storage can be found in the hyper-converged appliance space, with vendors such as Nutanix offering compute and storage appliances to provide a hardware-based approach to creating a virtual SAN. These virtual SANs and flash arrays are linearly scalable. In other words, when you need new capacity, a new server or appliance can be added, and its resources will automatically be added to the storage pool. This not only creates additional capacity, but also enables additional performance as the system connects to the Ethernet network at the same speed and capacity as the existing nodes. These next-generation storage systems are all scale-out systems, as opposed to the traditional scale-up solutions, which require the purchase of the next larger system when storage or performance capacity was exceeded. Next-generation storage systems are both high-performance and high-scale, and leverage the cloud scale economics of Ethernet and IP. The high-performance appliances and distributed scale-out architectures of modern IP storage present some unique challenges to the Ethernet network. In particular, the way the network handles congestion scenarios in high-bandwidth environments. While some storage protocols such as NFS can operate fairly well in a lossy environment, block-based storage is much less forgiving and performs optimally when there is no loss. Scale-out storage architectures often have traffic patterns which involve multiple hosts simultaneously transmitting to a single host. Scale-out ECMP architectures grow the width of the spine leaf network. This causes an increased probability of multiple hosts spread across multiple racks transmitting simultaneously to a single rack, and the likelihood of network-based congestion. This phenomenon, known as TCP incast, is a common cause of congestion, and as flows experience loss due to insufficient buffering, TCP connection collapse can result, causing significant performance drops across all flows. These drops, especially in a storage environment, can cause applications to become slow to respond or even fail completely. In addition, speed changes, such as those experienced when a flow originates from a 10 gig or 40 gig connected storage device to a 1 gig or 10 gig connected server, are also a common cause of congestion and can cause a similar collapse in TCP throughput. Technologies such as data center bridging and priority flow control serve to create lossless Ethernet-based networks and to alleviate the effect of TCP congestion collapse, but operate at layer 2 and are thus handled link by link. In a two-tier spine leaf network, pausing a busy uplink can have a detrimental effect to all traffic of a given class, as the pause frames are transmitted link by link towards the source or sources of congestion, slowing down all traffic along the way. So the burden is put on the switch architectures themselves to handle these congestion scenarios. Many widely deployed data center switches available today have shallow buffers, and utilize an internal cloth architecture to handle switching within the chassis. In these switches, congestion and pause can have a more dramatic effect, creating a condition referred to as collateral pause, where all flows are slowed down during periods of congestion. Due to the limited buffering capacity of these switches, this congestion situation can occur frequently. Arista's 7500R and 7280R series of universal spine and leaf switches follow the path of the award-winning 7500E and 7280E switches to provide a superior solution to handling critical storage traffic. The 7500R and 7280R series leverage the latest generation of merchant silicon to provide a dynamic deep buffer option for the highest performance data center switching, with up to 24 gigabytes of packet memory to handle the most demanding requirements put forth by next generation storage solutions. These deep buffers absorb the bursts present during TCP incast and when changing from high to low speed connections, ensuring fairness among all flows and minimizing drops. This translates to higher goodput for storage traffic, which translates to higher application performance. A major benefit of the use of IP as a transport for storage traffic is the scope of the networks. Fiber Channel over Ethernet, or FCOE, was an early attempt at providing a converged network infrastructure which saw limited adoption and suffers the major restriction of being limited to Layer 2 networks. As data center networks have embraced simpler two-tier architectures with the Universal Cloud Network, Layer 3 equal cost multipath provides vastly superior scale and availability to the data center, especially for east-west traffic, and protocols limited to Layer 2 have quickly fallen out of favor. The scale afforded by the Universal Cloud Network for east-west traffic is perfectly suited to IP storage traffic and is the model on which cloud architectures are built. Depending upon the customer's requirements, different options are available for architecting IP storage networks. Let's look at three of the most common examples of IP storage designs we see. The first design is what we call the dedicated storage rack. This design typically uses storage appliances, which are located in dedicated racks. Flash-based systems are often deployed in this manner, and often have higher bandwidth requirements because they are easily able to fill up 10 gig and soon 25 and 50 gig interfaces, providing high-performance storage access to the network. Likewise, the uplinks between the storage rack leaf switches and the spine typically run at 100 gigabits per second. In the dedicated storage rack design, TCP incast to the storage rack for write operations is a concern. As storage appliance connection speeds increase to 25, 40, and 50 gigabits per second and need to communicate with 10 or even 1 gig attached servers, the speed mismatch between storage and compute can be problematic. TCP incast and connection speed mismatch are both causes for congestion and see measurable benefit from a dynamic, deep buffered switch architecture like the Arista 7280R. The second design commonly seen is the converged storage rack. The converged storage rack is found where the customer is using a hyper-converged solution. Some examples of these solutions are Nutanix on the appliance side and EMC's Scale.io, which provides a software-defined storage solution. The converged storage rack typically uses systems where the compute and storage reside on the same hardware, either on appliances or on servers. However, designs where dedicated storage appliances reside in the same rack as the compute servers are also possible. Whether using dedicated storage appliances or hyperconverged systems, TCP incast can be an issue as multiple flows are likely to converge on a single system simultaneously. A deep buffered, high-performance leaf switch is beneficial in this architecture to absorb the incast, reduce drops, and increase application performance. The third design leverages a dedicated storage spine and leaf to offload the storage traffic from the rest of the network. Taking into account the significant savings achieved by moving from legacy scale-up fiber channel solutions to IP-based storage for large enterprise environments, savings can still be realized even when deploying a dedicated storage network spine and leaf. A dedicated storage spine and leaf provides protection against the influx of traffic which can arrive when the storage system needs to rebuild or rebalance the distribution of data across nodes. When a storage node fails, the data which resided on that server needs to be recopied for purposes of resiliency. To protect application data in flight, some organizations deploy a dedicated storage spine to ensure that all applications and storage receive the necessary network capacity to perform optimally. In the end, companies will build some or even all of these architectures and run them on the Arista Universal Cloud Network. Determining where a particular storage system should be placed in the UCN is a function of capacity planning. The ability to extract real-time performance data from the network switches is a critical requirement to ensuring that the storage network is being deployed optimally. Granular visibility into switch buffering at the microsecond level is needed to detect microbursts and engineer the placement of storage resources appropriately. Arista's LANs functionality provides this visibility into the switch buffers on the 7280R and 7500R products. Arista Networks is uniquely positioned as the technology leader for Ethernet-based storage architectures. Arista's 7500 series switches have long been the gold standard for data center spine switching, with the combination of density, resilience, programmability, and a robust system VOQ architecture in a modular system. Possessing the dynamic and deep buffers to handle both TCP incast and the speed changes common with 10 gig and higher connected storage systems, the 7500R series and 7280R series are uniquely suited to deal with all traffic patterns and application requirements. The VOQ architecture of the 7500R ensures fairness between all flows and eliminates head-of-line blocking and the possibility of collateral pause affecting flows which are not the cause of congestion. Visibility into the performance of the network is provided using telemetry tools such as Arista's LANs and using the openness of Arista's EOS to provide extensions such as the EOS Splunk collector so that intelligent placement of storage resources can occur. Installed in the most demanding environments with support for interfaces from 10 to 100 gigabits per second, the 7500R and 7280R are the best data center switches for IP storage networks. With leading storage vendor partnerships, Arista has the ecosystem, architecture, features, and expertise to truly transform the nature of data storage. It's time to move to the next generation of network storage.